So, we are looking at the properties of the solutions of the homogeneous second order linear equation. So, first property is that if you are given two solutions y1 and y2, you can make many solutions as you want as a linear combination of these two solutions. If on y1 and y2 are given, you can make c1 y1 plus c2 y2 as solution, where c1 c2 are constants. Okay, that is the first property I have given, simple property. The second one is, if I give you two solutions y1 and y2, they are linearly independent. When they are linearly independent, they will be linearly independent if and only if certain relation between them should be non-zero. That is what we defined as a Wronskian. Wronskian of those two functions should be non-zero. Okay, so that's what we have seen as a second property. They are linearly independent if and only if the Wronskian is non-zero for all values of x. That's what we have seen. So today we give property 3. That is, property 3 tells you that if the Wronskian is 0 at some point, that means Wronskian is 0 everywhere for all values of x. Okay, where x is in I, that is where the differential equation is defined, linear second order ODE whose solutions are y1 and y2. Okay, so if the Wronskian is at some point is non-zero, then the Wronskian is non-zero for every point. That is also true. Okay, so this actually tells you that Wronskian is 0 or non-zero at one point, then the Wronskian is non-zero at every other point. Okay, at every point it is well defined. So this is the formula we derive. This is called Abel's formula. So for that, we'll just start with the Wronskian of two functions y1 and y2, which is a function of x, which is, we define it as y1 y2 y1 dash y2 dash. This determinant, which is actually y1 y2 dash minus y2 y1 dash as a function of x. Now you simply calculate what are the given. So y1 and y2 are solutions of the second order linear ODE. So it satisfies y1 dash double dash plus px y1 dash plus qx y1 equal to 0. And y2 is also a solution of the second order linear ODE homogeneous equation. So it also satisfies this equation. So y2 dash plus qx y2 equal to 0. What I do is, I take these two equations, I multiply one with the y2, right hand side is 0. So if I multiplied the function y2, the right side is 0. This I multiplied with y1. Second equation I multiplied with y1. Now we take this difference, one minus other. So you will have a second equation minus first equation. So this minus this, if I take, so you will have y1 y2 double dash minus y2 y1 double dash is the first term. So this minus this plus px, which is common in both places of the each of the second terms. So you will have y1 y2 dash minus y2 y1 dash plus y1 y2 q minus y2 y1 q. So both are same, so it's 0. So that is 0, the difference is 0, so this is equal to 0. So this is exactly your Wronskian. This is your Wronskian. So I have px into Wronskian of x, which is equal to 0. So what happens to this term? So if you can see this one as a side, w dash of x, the ddx of the Wronskian, if you actually calculate, you will have a ddx of y1 y2 dash minus y2 y1 dash. So you can easily see that this will be y1 y2 double dash plus y1 dash y2 dash minus y2 y1 double dash minus y2 dash y1 dash. So this gets cancelled. What you are left with is y2 double dash minus y2 y1 double dash. So this is exactly is your w dash. So this is exactly what w dash of x. So I can replace this with w dash of x. So this is the first order linear ODE non-homogeneous linear ODE, okay, for x belongs to I. Wherever this differential equation is defined, that is where this Wronskian is also defined. So you have this first order linear homogeneous ODE whose solution you can simply calculate. This is exactly equal to z dw by dx plus px wx equal to 0. So this implies I can split, they are already you can separate the variables, these are all variables are separated, dw by dx equal to minus px wx. So I can write dw by w plus px dx equal to 0. This I integrate both sides from x naught to x, and because w is a function of x, I am integrating from x naught to x. Here also I integrate from x naught to x dx. So this will give me constant, okay. So let me call this constant log c. Sorry, this won't be, this you integrate from x naught to x dx, this will be 0 anyway. So this is equal to 0. So both sides, if you do that, it will be 0. So what you are having is log wx minus log w at x naught, this is w, equal to minus integral x naught to x px dx, okay. So this will give me wx by w x naught, which is equal to e power minus integral x naught to x pt dt, you can write, okay. So this implies wx is equal to w at x naught times e power minus integral x naught to x, p is the function given, so that is dt, okay. So this is called Abel's formula, Abel's formula. So this will give you a property that if the Wronskian is 0 at one point, see when I integrate from x naught to x naught to x naught is an arbitrary constant. So x naught is, you can choose x naught from the domain of the differential equation. So x naught belongs to I. You can choose any point, as x naught that belongs to the domain of the differential equation. So x naught, w at x naught, if it is at some point, w at some point x naught in I, if it is 0, if this is 0, wx is 0 for every x, okay. So this is true for every x belongs to I. So this is actually true, this is what you have the relation for every x belongs to I. So that implies if w at x naught is 0, then at some point x naught, then w at x is also 0 for every x in I, okay. So if this is non-zero at some point, then wx is also non-zero for every x, okay. So this gives you, so what is the meaning of w at x naught? That is w at x naught is, if you look at this, this is your this one, so this is your determinant. W at x naught is 0 means w at x 0 everywhere. So w at x 0 from the property 2, once w of x equal to 0 for every value, if and only if y1 and y2 are linearly independent, okay. So what we have seen is if wx is non-zero, if and only if y1 and y2 are linearly independent. So if w at x naught equal to 0, then w at x is 0 for every x, implies y1 and y2 are linearly independent, okay. So implies y1 and y2 are linearly dependent solutions, okay. So if this is non-zero, at some point, then w at x is non-zero for all points. That implies y1 and y2 are linearly independent solutions, okay, linearly independent solutions. dependent and independent. Okay, so that is your property number 3. So I have shown the property 3, that if it is 0 at one point, that means Wronskian is 0 at one point, means Wronskian is 0 everywhere. Implies from property 2, okay, from property 2, you can say that y1 and y2 solutions are linearly dependent. Okay, this is all you can conclude just by looking at this formula, Abel's formula. Okay, so you still don't know how to calculate, how to find the solutions y1 and y2, but if you know that your y1 and y2, if you know that you have two solutions y1 and y2, what we have is you calculate the Wronskian. Okay, you can actually calculate the Wronskian of these two solutions of the second order homogeneous ODE, linear ODE, as Abel's formula. If these solutions at one point, if the Wronskian is 0, that means Wronskian is non-zero everywhere. Okay, that implies they are linearly dependent. So this is how you can see that whether given two solutions of second order linear homogeneous ODE are linearly dependent or not. Okay, so if you are given two solutions, you can easily, by looking at its Wronskian, if it is 0, if just one point is enough. Okay, you can verify just one point these solutions, y1 at x0, y2 at x0. X0 can be any point in the domain of the differential equation. So verify that Wronskian. If it is non-zero, implies you can conclude that the solutions y1 and y2 are linearly independent functions, solutions. Okay, so we can use this Abel's formula to use this Abel's formula to get the, if you are given one solution of the linear homogeneous ODE, you can find the other linearly independent solution by just by using this Abel's formula. Let us see how it is done. Okay, so we start with, so we write the Abel's formula. Abel's formula is this. Abel's formula is y1 y2 dash minus y2 y1 dash. Okay, so this is all functions of x, because this is of wx. This is wx equal to w at x0. Okay, this is simply a constant, w at x0. Okay, so e power minus integral x0 to x pt dt. So what we do, so I know that if I divide this, if I divide this, with y2 square or y1 square, okay, so both sides you divide y1 square. So if I can divide with y1 square, provided y1 is, let y1 of x be a non-zero solution, of the ODE, linear homogeneous second order ODE. So what does that mean? So if it is a non-zero solution, y1x is not completely 0 for every x belongs to I. Okay, this is not 0. Okay, that is the meaning. That means you are given, see, you can see that in the plane, you know that two vectors are linearly independent. They are independent. Okay, so you know what is the meaning of it. Zero vector is always linearly dependent. So if you want one linearly independent vector, that means mathematically formal definition is, you can write some constant times that vector v equal to, if you want that to be equal to 0, if you can find such a vector for some non-zero c, then you say that v is linearly dependent. Okay, when is this possible? When this is 0, when c is non-zero, v has to be 0. So when v is 0, that means 0, 0, 0, that is linearly dependent, because 0 vector into some constant which can be non-zero. You can take any, simply for the sake of example as 1 into this is 0. So, I can find some non-zero C such that this vector equal to 0. Okay? This is what is the meaning. Otherwise, if you cannot find such a C, so implies if you make this CV0 implies C equal to 0, that means V has to be linearly independent. That is possible only if V is non-zero. Okay? Only if V is non-zero, you can say that the vector V is independent. V is linearly independent. Okay? I write Li as a linearly independent vector. So, same thing is true here. So, once it is non-zero, this is linearly independent function. So, y1 of x is linearly independent solution, solution of the ODE. ODE means second order homogeneous linear ODE. Okay? So, once it is given, if it is because it is non-zero, I can divide, assume that is you can divide this is non-zero everywhere in the domain. So, y1 x y2 dash x minus y2 x y1 dash x. I divided both sides with y1 of x square. Okay? So, w at x naught. So, w at x naught is actually constant. So, some arbitrary constant. So, you can fix any x naught, w x naught is the solution. So, it is an arbitrary constant basically. The way you solve this equation here, this is w x naught is actually constant, that is actually an arbitrary constant. Okay? W x naught. So, it is a constant e power minus integral x naught to x pt dt divided by y1 of x this square. I square both sides, and this is exactly, this is now in an exact form. So, the left hand side I can write this as derivative of y2 by y1, right. So, this is exactly equal to this. Right hand side as it is. Right hand side you see this is a constant and this is function of x and this p is given. So, this is a function of x, whole thing is a function of x. Okay. So, I can now simply integrate from x naught to x. Okay. Say integration from x to x naught to x gives, what do you get? So, x naught to x d dx of y1 y2 by y1. Okay. So, this this is a function of x. So, you are doing it with respect to x. Okay. So, this is equal to, now the right hand side is this, w x naught is constant, you are now integrating from x naught to x. This is now, x is a dummy variable, I can write simply e power integral x naught to some t p. Now, inside this integral I make t as a dummy variable. So, ds divided by y1 of t square. Now, this dt. Okay. This if I integrate this function of t with respect to x naught to x. So, same thing I can do here. So, I can make this as a dummy dt. So, dt, because I am integrating from x naught to x, inside integrand I can make as a dummy variable. You can keep also x also, no issues. Okay. So, this is what you have. So, this will directly give me y2x by y1x minus y2 x naught by y1 x naught. What is this one? So, this is equal to w at x naught times x naught to x, whatever this function. So, 1 by y1 of y1 square of t e power minus integral x naught to t ps ds. This is a function of t, so you have dt. So, this is what you have. So, this implies y2 of x equal to, so this whole thing is a constant. Okay. So, you can take it as a constant because you are solving differential equation for y2 by y1. So, y2 by y1 at some point is be arbitrary constant. So, this will be equal to y2 by y1x equal to some constant times constant, I take it c plus w at x naught into as it is x naught to x 1 by y1 square of t e power minus integral x naught to t ps ds into dt. So, if I multiply both sides y1, I take it to the other side, this will be c times y1 of x, this will be y1x. So, that means w at x naught into this is constant times y1x. So, this is what you get as a solution, second solution y2. So, I found my y2 as, because y1 and y2 are two linearly independent solutions in your Wronskian, we started with the Wronskian from the Abel's formula. So, what is y2? y2 is actually solution, second solution. You can easily see y1 is a solution, you can take, you can ignore this term because you already know that y1 is a linearly independent solution, and what you are left with the second solution is this one, is w x naught is a constant, w at x naught times y1x into x naught to x 1 by y1 square of t e power minus integral x naught to t ps ds dt. So, if you look at this integral, this is a function of x, this will never be 0 because it involves integration with respect to exponential function, exponential divided by y1, okay, y1 square. So, this will never be 0. So, if you see y2 by y1, if I divide y2 by y1, which will never be constant, it is not a constant. y2 by y1 is not constant means y1 and y2 are linearly independent, since y2 by y1. So, from this y2 by y1 is not a constant, y2 is, the way you define this y2 is second linearly independent solution, second solution, that means that is y1 and y2 are, or you can directly write. So, constant y1x comma y2x are linearly independent solutions. Okay. So, you have found, if you know one solution, assume that you can divide it, okay. Assume that it is non-zero at every point of the domain of the differential equation. If you divide it, what you derived is from the Abel's formula, you get your second solution y2. Because it is a homogeneous equation, constant times the second solution is also a solution. So, you can ignore this constant. Reason is, if this is a solution, is constant, any constant times of is also is a solution. So, we are discussing about the properties of solutions of second order linear ODE, homogeneous ordinary differential equation. So far we have seen three properties. One simple property, linear combination of any two solutions if you give is also a solution. Two solutions if you give me which I can say linearly independent if and only if the Wronskian is non-zero. Okay. The third property is the Abel's formula. If the Wronskian is at one point is 0, Wronskian is, if it is 0 at one point, Wronskian is 0 everywhere. If it is non-zero, Wronskian is non-zero everywhere. Implies you can conclude that those functions, solutions y1 and y2 are linearly dependent or independent. So, we have seen what is Abel's formula by considering a differential equation, linear second order homogeneous ordinary differential equation, for which if you know one solution y1x, you can find the other solution, other linearly independent solution through this formula, Abel's formula, that is y2x is given in terms of y1x into some integral that involves 1 by y1 of x, y1 of t square. So, you have 1 by y1. So, that means the first solution should not be 0. So, all those points at which first solution is 0. So, that means it does not make sense if it is 0. Okay. This formula does not make sense, Abel's formula does not make sense if y1 of x is 0 at certain points. Okay. So, those points you can remove from the domain of the differential equation and consider the differential equation. For example, you see that you take the domain, you take this domain, and then so if y1 is 0 at some point, for example at 1, okay, that is what we will see later on with an examples. Domain of the differential equation is 0 to 2, okay. Then and suppose y1 of x is 0. So, in this for example, your solution is 1 minus x, y1 at 1 is 0. So, in that case this formula does not make sense. So, what you do is you consider the differential equation in this interval and in this interval 0 to 1 and 1 to 2 separately, so that y1 of x is non-zero in those two intervals. So, you consider the differential equation, consider your solution y1 of x in the domain 0 to 1 and get y2 in that domain. Similarly, you consider y1 of x in 1 to 2 in the interval 1 to 2, and then you from the Abel's formula you can get your y2 of x in the domain 1 to 2 in the open interval 1 to 2. So, what happens if you consider what happens at x equal to 1? y1 of x is 1 minus x in 0 to 1 and also y1 of x which is 1 minus x, same 1 minus x in the domain 1 to 2. It is actually a continuous function. So, at 1 y1x is defined, it makes sense. So, y1x is actually a solution we have seen already. Okay. So, same way now y2 you found whatever you find here and here. Okay. If it is continuous, if what you will see is that because it is an integral, y1x is continuous, you can see here. So, y1x into some integral. So, integral is a continuous function, integral some fixed point to x. So, this is actually a continuous function, okay, because of this integral, in fact differentiable. Okay. So, because of this you see that after getting this your solution y2 in each of these intervals, you can see that it is a continuous function. So, at 1 you simply take the limits, the limit x goes to 1 from left hand side will be same as limit y2 of x as x goes to 1 from the right hand side, both are same. So, at 1 also it is defined. That is how you have to see this Abel's formula, that is valid in the full domain 0 to 2. So, this is how we will see in the examples when y1 is 0 at some point, and how do you find y2. Okay. Even though it makes sense, it does not make sense at those points, we will just put it in the formula and get your y2, so that actually works. Okay. So, this is how you can get one solution, second linearly independent solution once you know one solution, one non-zero solution y1 of x. Okay. And then how do you say that? So, we have also seen that this is a y1 times something which is not constant, because the integral x naught to x involving y1 integral. So, it is non-zero, it is non-constant. So, that implies y2 by y1 is non-constant, that means it is they are linearly independent. So, this is what we have seen. We will see with an examples in the next video. We will try to give you, we will demonstrate in the next video with examples how to get the second linearly independent solution once you know one solution y1 of x. Okay. Thank you very much.